Okay, so let's continue number 9. Recall this is our recurrence relation that we obtained right in the last part. And I just added this constraint, right, because n has to be at least 0 in order to find our CNs, right? We're not working with C sub -3, for example. So if n has to be at least 0, so let's explore this pattern. If n is 0, again, I'm just inputting 0 for my n's. So I have, okay, 0 plus 1, so C1 equals C naught, 0 plus 2, so 2 over 1 if you want to write that. So I'm just left with 2C0. And let me just go ahead and write it in. C1 is, just so we can have a nice clear relationship, C1 is 2C naught. If n is 1, then this is C1 plus 1, so 2. C1, and then I have 3 over 1 plus 1 is 2. So I have 3 halves C1, but again, we know what C1 is, right? So right here. So C1 is 3 halves times, well, let's go ahead and write 2C naught, and that just gives us 3 C naught, right? Because we want to find these relationships in terms of C naught. So there is C2, and if n is 2, let's see, we get C3 equals C 2 plus 2, so 4 and 3. Okay, so we get 4/3 of C2. But again, what's C2? Well, we just found C2. So that's 3C naught, and this is nice. And we end up getting C3 is equal to 4 C naught. And let's just go ahead and find one more. So if n is 3, then let's see, what am I getting? 3 plus 1. So I get C4 is equal to, looks like 5C3 over 4. Okay, so we get 5/4 of C3, which again is right here. So 4C naught, and this is nice. We get 5C naught. So C4 is 5 C naught. So even if we found some values, right, and we can continue this process. If you're having trouble seeing the pattern, then again, feel free to find a couple more values. Okay, so I'm going to go ahead and write my C1s nicely, and just so we can see this vertically, it's easier to see the pattern. So we have C1 is 2C naught, C2 is 3C naught, C3 is 4C naught. So this pattern is not very difficult, but I mean, you'll have some challenging ones on your homework, and if you're having, again, trouble seeing it, make sure to write it, just organize it, and it'll help you see the pattern. So 5C naught, right, and I mean, we can kind of figure out what C5 is going to be. Well, notice, right, this is just greater than 1, right, 2 plus 1, 3 plus 1, 4 plus 1. So this is probably going to be 6, right, C naught. And eventually, Cn is going to be, well, again, what's the relationship between this subscript and this number, right? The difference is 1. So it's probably going to be n plus 1 C naught. Okay, so that's our Cn. And again, we assume that the solution was a power series representation. So remember, we assumed Cn x to the n. And again, this is just C0, right, x to the 0, which is just 1, plus C1x plus C2 x squared plus C3 x cubed plus, well, dot, dot, dot. Okay, so we found our CNs, right? We have, well, we know it's C naught is just C naught, C1, C2, C3, right? They're all right here. So let's just go ahead and substitute these values. Make this a little bit bigger. Whoops. Okay, so we have, let's see, we have c naught plus 2 c naught x plus c2, which is 3 c naught x squared plus c1, c2, c3, c4, you can write it in, 5 c naught x, let's see, c1, c2, c3 is 4. Oops, I skipped one. So 4 c naught, and this is x cubed plus, okay, dot, dot, dot. And notice, right, we have a c naught here, so we can factor that out. And we're left with 1 plus 2x plus 3x squared plus 4x cubed plus dot, dot, dot. Okay, so we have this, we found a power series representation, right? This is an infinite sum, and it's definitely a power series. But what does this remind you of? So this part, right, this is where you, you look at page, 195 in your book, and, does it remind you of any of the power series in there? Does it look exactly like one of them, or maybe we can, kind of modify this to make it look like one of them? And the one I'm looking at is, I'm looking at 1 over 1 minus x, right, which is our geometric series, which we've worked with before, or I should have done an example, hopefully, but it doesn't look exactly like it, but it's very similar to this. So I'm just writing this down. And, I mean, what do we have? Well, this is 1 plus x cubed, x squared plus x cubed, and so forth. And then here we have 1 plus, well, not necessarily x. We have 2x, not x squared, but 3x squared. So how can we maybe obtain this from this? Well, I mean, we know how to differentiate. So what happens if I take the derivative of this guy? Well, I mean, the derivative is, we have our terms here. So the derivative of the 1 is 0. Of x is 1, plus the derivative of x squared is 2x. The derivative of x cubed is 3x squared plus dot, dot, dot. So notice that it's right here. So it's the derivative of our 1 over 1 minus x. So we can rewrite this as, so I'm just kind of continuing here. So our y of x is going to be equal to c naught of 1 minus, actually, whoops, there's my eraser. Okay, it's not letting me erase. So I'm going to write 1 over 1 minus x, right? But it's really the derivative. But we don't want to write this in terms of, we can simplify this. We can actually find the derivative, which we did here term by term. But, if we actually found the derivative, just like we did in Calc 1, what would we get? So if we actually do the math here, so the 1 over 1 minus x is really 1 minus x to the negative 1, right? That's 1 over 1 minus x. So if I differentiate this, so this is a prime, right? And that's negative 1. So using the chain rule, I get negative 1, let's see, 1 minus x, I'm subtracting 1, and times negative 1, right? Using the chain rule. So then I get 1 minus x to the negative 2, which is just 1 over 1 minus x squared, right? So this guy, this guy is really this guy, which is really this guy. So let's replace this this expression. So we have, okay, y of x equals c naught times 1 over 1 minus x squared. Okay, so we have identified, right, a series solution in terms of familiar elementary functions, right, in terms of 1 over 1 minus x. Now let's find let's see, the next directions is the radius of convergence. So let's quickly do this one, which is kind of a nice one. So it's rho equals the limit as n approaches infinity, right, of our cn's over cn plus 1. So the limit as n approaches infinity, well, what's our cn? Well, remember our cn was right here, right? It's n plus 1 times n naught, or times c naught. So that's our cn. So n plus 1 c naught. So n plus 1 times c naught, and I'm dividing it by cn plus 1. Well, that just means I'm replacing n plus 1 for n plus 1 c naught. And this one's nice because that's going to be gone. The limit as n approaches infinity. And what do we have here? We have n plus 1 over n plus 2. And this is nice because we can divide each term by n, right, or multiply by 1 over n. And that gives me, to help us evaluate this limit, we get 1 plus 1 over n all over 1 plus 2 over n, right? So divide each term by n. And the reason I did that is because now when we take the limit, right, the limit as n approaches infinity, right, this guy goes to 0, this guy goes to 0, right, because 1 over n, right, or 2 over n, right, looks something like this. And so as n approaches infinity, right, this function slowly, gets closer and closer to 0, right? And, there's a horizontal asymptote at on the x-axis, which, again, never touches 0, but it gets close to 0. So then we're just really left with the limit as n approaches infinity of 1 over 1, or of 1, but we know that the limit of a constant is just the constant. So here our radius of convergence is 1.